Hi, my name is Julia Silge, and I am a data scientist and software engineer at Posit, formerly RStudio. And today in this screencast, we are going to use a recent Tidy Tuesday dataset about a citizen science project for bird science. It's called Project Feeder Watch, and we're specifically going to use the data set that is about the sites where the bird feeders are. We're going to build a model to predict whether a squirrel comes and eats the bird feed from that site. One thing that this problem exhibits is class imbalance, because it turns out there's a lot more bird feeders that do have squirrels than that don't have squirrels. And so we'll have to decide whether to try to use some kind of feature engineering approach to address this, and then understand how this may affect our results. Let's get started.
All right, welcome. Let's get started. So today like I said in the intro, we are going to look at this data from, it's actually last week's Tidy Tuesday when I'm recording this. It is about bird feeders. There's a citizen science project dealing with bird feeders, and there's a couple of different data sets that are part of this week's Tidy Tuesday, but this one is the one that is about the sites where the bird feeders are. So, people participate in this, like, submitting reports about how many birds they see and what kind they are. But this is the information about the sites where there are. There's a whole lot of information about these different feeder sites, like what kind of yard type there is, what kind of habitat, trees and shrubs. Are there cats and dogs around? Are there humans around? And then, like, when they do the feeding, and the number of feeders of various kinds, population and whatnot. But oh, look what we have here. Squirrels. So for the rest of this screencast, let's pretend that you hate squirrels. So we hate squirrels, and we just hate it when those squirrels come to our bird feeder. So let us build a model to predict whether a squirrel is going to come and eat at your feeder based on the other characteristics of the feeder. So let me add, I'm just going to put this straight here. Let's say squirrels equals, I'm going to use if else. Because see how these are all, these are ones and zeros, and then, like, they're indicator variables or dummy variables, and then some of them are actually numbers, like the numbers of feeders or the population around it. I think there's some other things like housing density, but a lot of these are zeros and ones, which mean like yes, no. So let's say if else on the squirrels, and let's replace those ones and zeros so that we can make some plots, and then we can build a model. So let's say, if it's 1, that's squirrels, so yes, and if it's 0, that's no squirrels. Hopefully I can spell this. Okay, let's just read that one more time and change that, and then let's see what the distribution of squirrels is. Like so. Okay, so here's what we have. We have there's a fair amount of NA here, and you can see this. There's a fair amount of NAs in all of these. But here we've got a fair amount of missing data, and then we have a lot of squirrels, and then much fewer no squirrels. So this is what we call imbalance data. There's more than 4 times as many sites that have squirrels than don't have squirrels. So if we're these squirrel haters, if we just hate the squirrels, wow, we're in bad shape, because there are so many of these bird feeder sites that have squirrels. So let's try to build a model. We're going to build a model that predicts, okay, what keep the squirrels from being around at my bird feeder site. So let's do some exploratory data analysis first. So we're gonna filter the non-NA data, and then let's go group by squirrels, and then let's say, whoops, did I do this wrong? Too many M's. Let's look at like, one of these things, like say, the number of nearby feeders. So this one is a number, right? Like, is it 0? Is it 1? So let's say nearby feeders, and let's take the mean of that. So this is NA, because remember, there's a lot of NA data in here. So we're going to say NA remove. So here we see that the higher the average number of nearby feeders is, then that's more associated with squirrels. Whereas if there are fewer nearby feeders, that's associated with no squirrels. So these are the kind of relationships we're going to try to explore and to take advantage of when we build a model. Let's take, like, there are some of these that have like whole things together, like yard or habitat. Let's do a little bit of some analysis where we look at all of those at once. So let's do this. The same thing we did before, group by squirrels. And then let's do summarize. We're going to do summarize with across. So I'm going to say summarize across everything that contains, let's do the habitat like that. And then when we're going to take everything that contains hab like this, and then we're going to take the mean of it. Again, we have many NAs, so we have to pass in NA RM equals true. And so now we have these percentages here, these proportions. So let's pivot longer. We're going to pivot longer everything that has that habs in it like this. And because we're heading towards making a visualization here as we start. I want to take away all that hab. So I'll say string remove hab, name. And then let's remove the beginning of that hab underscore like that, because that will make a nicer visualization. And then now we start the plot. So we're going to put on the x-axis, let's put value. On the y-axis, let's put name. Say fill equals squirrels. And let's make a bar chart with geom call. I like it to be a little bit transparent, and I think we'll need to say position equals dodge like this. So let's look at that. This is a fair amount of data, so it's taking a little longer than I expected, but there we go. Okay, that was a little slow. Okay, so let's improve this plot just a little bit. So I'm going to say this is the percent of locations of the sites that we're dealing with. I don't think we need the y-axis had to have a label. I don't think we need fill to have a label. And then let's go in here and let's reorder this. So I'm going to use fact reorder. Like here, so instead of in alphabetical order from bottom to top, it's going to be in order of the value, the percentage here. So let's try this. There we go. Okay, so what does this tell us? So the proportions here is how many of these sites have this true. So lots of the sites are residential, which makes sense because this is citizen scientists, reporting about the birds. So it makes sense that most of them are residential. Then we have things like woods, freshwater, more woods, deciduous woods, and we go down. Like the most rare down here are like saltwater areas and orchards. But then if you look at the difference between the two, between the squirrels, no squirrels, it's like what proportion of the group of squirrels versus the group of no squirrels are in these. So as we can look here, we can see that proportionally the residential area has more squirrels. Whereas we look for another one down here, proportionally the agricultural area has fewer squirrels. Like there's more no squirrels than squirrels. And if we keep going down here, evergreen woods is about an equal proportion. And then like in the desert, there are many more feeder sites that have no squirrels than have squirrels compared to the other kinds of sites that we have. So, right, fewer squirrels in the desert, right, which makes sense. So this is the kind of, like, maybe we can use this kind of relationship as we build our model. Our model will learn from this. Okay, I think that's pretty good for EDA for now. And let's get started now building a model. I'm going to load the Tidy Models meta package. I'm going to start by splitting my data. And one thing that occurs to me as I'm saying this is that these sites probably have some spatial information. Actually, when I look here with like the deserts and the residential areas and whatnot, and so one could maybe argue that we shouldn't do just plain splitting and resampling. Maybe we should use spatial resampling. I think I'm going to not get into that right now because we're going to focus on the downsampling, the subsampling issue that we talked about in the intro. And so I think I don't want to go into that right now. So we're going to take this more basic approach. I'm removing here some of the ID variables because I don't really need them in my data while I'm fitting. I'm also like whether it's fed year round or fed in all the months, I feel like I could either remove all of these or I could remove this because that information is there. Let's just take that out. I think I would be more comfortable if we took that out because that's like information that are containing some of the same information there. What happens if we do select squirrels and then everything else? So, whoops, everything is a function. There we go. Okay. Look at all these NAs. Are there any that are all NA, I wonder? Let's say, especially once we take out things where that have no NA for squirrels, let's say select where all is NA dot, like that. I need this. Okay, so that's fine. Maybe there isn't anything with all NAs. I'll pop something into my feature engineering recipe that should take care of that if we have that. Okay, great. So I can pipe this straight to initial split. So this is a function that splits my data into training and testing. I'm going to create a split object here that keeps track of which observations go into which data set. So this is a big data set. And now let's create our training set. We will do the same thing for a testing set. And then, then let's create some resampling folds. So I'm going to call it feeder folds, like here, and I'm going to use vfold cross-validation. I'm just going to use the default here. Let me pass in the training data. This is what we create a resampling with, and I'm going to stratify again here. All right, let's run all that. Okay, so yeah, these are big data sets, right? And again, I might be ending up with slightly optimistic results at the end because I'm not splitting my data with awareness about the spatial data, but let's just kind of put that to the side and keep going with that knowledge. If I were to improve this and do a better job, that would be something I would look into. Okay, so now let's talk about the feature engineering. Let's look at the training data one more time. Feeder train, like so. Okay, so this is this is what we're going to predict whether there's squirrels or no squirrels at that feeder site, and we're going to predict it with all this other information. So lots of columns, lots of rows, pretty big data set, but lots of NA values here. So let's start this. So we're going to say, let's make a recipe. We're going to predict squirrels with everything else, because I removed these things here that were more like IDs before I did the splitting. Let's pass in some of the training data like so. And now let's say what are we gonna do for feature engineering? I need to handle all this missing data. I'm going to impute those values. There's a ton of it, like all over, and all kinds of different variables here. So I am going to use a pretty simple imputation approach. I'm going to impute I think I'm going to impute the mean, because these are like zeros and ones. If I impute the median, it's just going to put the most common value in there and get even more skewed in distribution, whatever. So I'm going to impute the mean, even though that's not a real like value for most of these. This could have, like, you can't have, if you're like, are there dogs there? You can't have like, well, it's 0.2, but that's okay. I think this seems like the best option for what I should do here. And then I am going to remove things that have zero variance, which I hope includes NA values. I think it does. I think we're good to go there. Okay, so let's call this the recipe, like here, the feeder recipe, like that. So if we look at it, it's got 2 steps that are added here. I can prep this to make sure that it works correctly. Like so. So now it's actually estimating, like it's imputing everything. It actually did not remove everything. Maybe it doesn't have all NA values. We'll just keep an eye on that. Okay, so remember this though. When we counted the squirrels, is quite imbalanced. So what I want to do, let's call this our like starter recipe or basic recipe. And I want to try to fit a model with this recipe for feature engineering or pre-processing. And then I also want to fit one that uses downsampling to account for this class imbalance, where what happens is every time, let's look at the training data. That's a better thing to look at. So every time I look at the training data, maybe like a resample of it, when I look at it, I'll say, I have this many examples that are no squirrels. So I will go here and I will only keep 33,992 of these, and I throw the rest of them away. And then I go to and the next time I make the training set, I do the same thing, like over and over when I make these resamples. And what we're going to look at is what kind of results do we get when we keep all the data, including all these squirrels, all these hateful squirrels that we can't believe are coming to eat from our bird feeder. And when we throw out a good chunk of this data, what are the differences? What do we see are the differences there? The way we go about doing this is with the Themis package, which is a extension package for recipes. And what we do is we add another step downsample, and then we give it the outcome so that it knows how to what do we want to balance? Like what am I throwing away so that I have the equal proportions of this, like this. So we're going to compare the feeder recipe together with step downsample. We do need a model. And what I'm going to use here, so this has quite a lot of columns. And so what I think I'm going to do is I'm going to use a regularized regression model that will use regularization to reduce how many of these features. Like, it will use this algorithm to decide which of these features we want to keep, are important and are informative, and which of them are we going to are we going to not use and keep in the final model? So I'm going to use GlimNet for that. So I'm going to create a model specification here. I am going to say logistic reg because I'm predicting a class, like a 2-class label, squirrels versus no squirrels. I am going to tune the penalty. So the penalty is that how regularized is the model, and I don't know that ahead of time. That's going to be a hyperparameter of the model. And then I am going to use mixture equals 1. When this is the L1 versus L2 regularization. And so by mixture equals 1, that's a lasso model. So I'm doing lasso regularization. And I need to set the engine to GlimNet. So now what I've done here is I have created a model specification so it's a tunable model specification for regularized regression, i.e. the lasso in this case. Okay, so we have a model. We have a model. We have a feature engineering recipe, but we actually really have 2 feature engineering recipes, and I want to compare them. I want to see how they're different from each other. So a great way to do that with tidy models is something called a workflow set. So a workflow set is a way to combine different model workflows together and then safely and efficiently tune or otherwise compare them. So the first thing we pass in is the preprocessors. So that's a list here. So let's say it's a named list. So I'm gonna say basic equals feeder recipe here, and then I'm gonna say downsampling equals this, what I said right here. So I'm one of them is using just my basic recipe, and then one of them is adding in downsampling. And then I add in the models. So I'm gonna call it the GlimNet, and what I pass in is the GlimNet spec right here. So let's call this a workflow set. This is my workflow set. Maybe I should call it like feeder set or something like that. I'm just gonna do this. Like so. So there are 2 options in here. They have the same model, the same GlimNet model, but they have different feature engineering recipes. A workflow set can have many more workflows in it than this one, but we're just going to use 2 to compare it to each other. So now that we have this, we need to tune them, because remember there's nothing tunable in our recipe, but there is something tunable. We have to know the right value of regularization for our particular data that we have here. So let us set this up. So I'm going to remember to turn on parallel processing. I'm going to remember to set my seed because this involves randomness. And then I am going to call workflow map. So the way workflow map is, first you pass in your workflow set, like so. Then you say what function you want to use. I'm going to use just basic tune grid. Then I pass in things that I need for the tuning, like I need to pass in my resamples here. So that's super important. I need to pass in how many values for this penalty do I want to try? Let's try 15. I could not pass in any metrics, but I actually am going to pass in a whole bunch of metrics because I want to very thoroughly understand what kind of difference the downsampling makes. So we're going to keep accuracy, which is like a typical value, like a typical metric for these are like the 2 basic metrics, the default metrics in tidy models for classification models, but let's add in more. So we can add the log loss, which people like to use it because it is for the model as a whole, but it measures how wrong you are. So like if it truly has squirrels and you predict a value of it, will, like what log loss does is it says it helps measure that you do a better job at when it's, say you predict a probability of 0.9 versus a probability of 0.6. Both of those would, give you to the majority class, the positive class, whatever one is. But it is able to say like how wrong were you. The next things that we're going to do are sensitivity and specificity. These are metrics that are about one class versus the other. Like, how good of a job do you do measuring the positive class versus the negative class? And so that will be important here when we're looking at this imbalance data set. I'm also going to pass in some params. The reason I'm doing this is because the default for penalty is really broad. I know this just from like experience with it, but like for the default for penalty is just like really, really broad, and I want to make a narrower penalty. So I do this. See, it's like minus 10 to 0. I don't need that at all. I'm gonna do like minus 3 to 0. Much, 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 much smaller. So, and then what I put here is the parameters for the narrower penalty like this. Okay, let's assign this to something. Tune result. Okay, and let's kick it off. Okay, while it's running, let's just do a reminder of what it is that it's doing. For the workflow set that I had, which has 2 different possible model configurations, I'm tuning over a grid. I'm using the 10-fold cross validations to tune. The grid that I'm turning over is actually more like a set, a vector, I guess, because I'm not doing some like high dimensional grid of many hyperparameters. I only have one hyperparameter that I'm tuning right here. So I'm trying 15 possible values for the hyperparameter, which is the penalty, the regularization penalty. As I'm tuning, I'm storing many metrics, not only the 2 default metrics that we have here that we always get, like if we don't specify anything, but some other metrics as well to be able to look and see what's happening. And I also did set a non-default set of parameters for tuning, just because I know from experience that the default penalty range is very broad for a lasso model, and I probably don't really want to do that. Okay, this is fairly big data, and I am training 15 times 10 times 2 models. So, oh, if it did finish. Okay, but let's do that. So well, how many models did I train? 15 possible hyperparameter configurations times, oops, where's goodness the times, times 10 cross validation folds times 2 different configurations. Like one of those models it used my basic recipe, and one of them used a downsampling recipe. So I trained quite a lot of models on quite a big data set, but it did finish, so we can keep going. All right, so the first thing I'm going to do here is use the auto plot method on these results to see what I get. Whoops. All right. In this case, I did 5 metrics. I should have done 4 or 6. Oh well. Okay, let's just get rid of that legend, because in this case, it is not helpful. And let us zoom in here and see what we have. Okay, so what's on the x-axis? It is the workflow rank, meaning like which workflow are we on. The y-axes here are these metrics. So we can get pretty good accuracy, but if you look up, when we get pretty good accuracy, the sensitivity is basically 0. And the specificity is really high. So when we're in these low rank results, we get great, or pretty decent at least accuracy, but at the expense of terrible sensitivity and like near perfect specificity. So when you see that, what you realize is I'm just predicting everything into one of the categories. I'm just predicting everything to be the majority class. Every site that I'm looking at, I'm just saying squirrels, yep, squirrels all the time, squirrels. Okay, let's keep going and see what we do for the later workflows that we tried. If we don't want sensitivity to be 0, we can have it up here, 6.6 something, 60% or something, and specificity is about the same. So in this section, we see that we can get sensitivity and specificity that are about the same. If we go up to perfect sensitivity again, then oh look, specificity dropped to 0. So then we have the opposite problem, you know. So these intermediate ones are the ones where we are able to identify both the positive and the negative class. In many problems, like real world problems, it is important to measure both. Sometimes though, it's much more costly to measure one of these wrong than the other. And so there's no right answer as to which metric is right to use to evaluate models. Instead, you have to look at it holistically at a bunch of different metrics and be able to understand which are important for your use case. Do notice accuracy takes a big hit when we do that, and in fact goes down to a terrible value down here, which is probably when we are predicting everything to be the minority class, no squirrels. And we see, you know, like some similar kind of things happening on these other metrics. So that's pretty interesting to see. Given that we saw that, let's dig a little deeper into these results. So we can use this rank results function, and we put in the result that we have, and then we can set a rank metric. So what happens if we say sensitivity? This is this one where we say I want to be able to measure the negative class. I think I said that right. We can see here that maybe as you may have guessed, these are the ones that did use downsampling. Now, if we do the same thing, but like, what if we were to use a metric that looked at the model as a whole, not at just the hard class to be able to measure? Perhaps you are not surprised to see that then I am dealing with the basic recipe, that one that did not involve downsampling. So when we do downsample, we are able to measure both classes. But if you're looking at a metric that, like if you were just to literally ask what has the best log loss, you would not choose downsampling. Instead, you have to look in more detail to be able to do a better job there. You have to look in more detail to understand what it is that you want to do. Okay, so let's say for our use case, it's important to us not to just predict all squirrels or no squirrels. I want to be able to understand both. And so what I want to do is I want to take this one, downsampling GlimNet. So what I can do if I want to, look a little bit more in detail and like look at the tuning results that I spend so much time working on, I can use this function extract workflow set results, and I can put in the name of it, downsample GlimNet. Down tune rs extract workflow set result down sampling. And so these are the tuning results for my my recipe that involved downsampling plus my GlimNet model. So let's say I call this my downsample results, like this. I can auto plot this downsample like so, and this will pop up. And let me zoom in because this is big. I've got a lot of metrics on this. Like so. So let's look at how these change with regularization. So on the right is a lot of regularization, meaning just throw predictors out. Just throw them out willy-nilly. I don't want them. On the left is low regularization, meaning I am not going to throw many predictors out. I am going to use all or many of the predictors. Notice that accuracy is high and then drops. So remember, this is with downsampling. It's high, it drops, and then it kind of bottoms out. Log loss starts low, which is good. It's lowest over here with a tiny bit of regularization, and then increases and then flattens out. So this is bad over here. ROC does the same thing as accuracy, which like it often does. And then let's look at sensitivity. Notice that it's okay, or it's like, a good-ish value. And then as you regularize a lot, it goes way up. It's perfect, which of course means that specificity has gone down to 0. So specificity is, decent, and then drops to terrible. So which of these regularization parameters do we want to pick? We could pick the best sensitivity, but then we would get 0 specificity, which is kind of the opposite problem of what we were trying to avoid to start with, was like perfect specificity and 0 sensitivity. We could go in and pick the best accuracy, or log loss, or ROAC, or ROCAUC. That seems like a good option to me, is to use one of these 3 metrics to choose the best model. But one of the reasons we use regularization is try to get to simpler models. So I might not want to use the best value for accuracy, but rather the simplest model that gives me results about as good as the best model. And I can do that using this function. So I take downsample result, and then I can use one of these functions, select by % loss or by 1 standard error. I'll do this. This is like a rule of thumb of a way to pick a simpler model that performs about as well as the best model. So I'm going to say minus penalty. So that means what I'm saying is, like, I want a big penalty. Give me the biggest penalty possible. And then I have to choose a metric. Remember I said I want one of those metrics that's about the model overall, both the positive and the negative classes. Like maybe I'll say the log loss here. And so this gives me this penalty right here. It says this is the biggest penalty where you get log loss that is about the same performance as the best value. So I could call this best penalty, but that's best, not meaning like the one that gives us the best performance, but the best by my rule that I have here about how to choose. Maybe it would be good to call it, maybe I should call it simplest penalty. I don't know. I'll just call it best penalty. Okay, so this is the penalty I'm going to use. And now I can go back into my original workflow set and update it. So if I take that set that I had and there's these functions that can handle, like, pull things out as you want. So if I pull down the same thing here, this is a workflow that is untrained with a recipe, with the downsampling, and with the model, but it's tunable right now. So I can finalize this workflow with this penalty value, like so. And now instead of saying tune here, it has a real value. So this is the penalty that I identified as the best one for me to use, because it's pretty big. It's the biggest I could get without losing a lot of performance. And then I can pipe this to last fit. And so what last fit does, it's like a convenience helper function that fits one time to the training data and then evaluates one time on the testing data. And remember that the split object has both of those. This is the first time that I am using the testing data during this whole time. So let's start this. So it's fitting one more time. So it's going to take just a moment. Again, it's going back to that big training data set, fitting the regularized classification model that I have with this penalty I chose. Okay, so this is a tibble that has a bunch of stuff in here. So what is in the workflow is trained using the training data, and then these predictions and metrics are all from the testing data. So for example, I can pull out the metrics. I can say final fit like this, and it will compute these basic metrics for me. I can I can get out the predictions. And then once I have the predictions like this, I could compute the log loss again, where I say the real value squirrels and then pred squirrels, I think. Whoops, I have to do the other one. You do unfortunately have to get these right, or the value doesn't mean anything. So this is the right one. This is the base level because N comes before S. So it's in alphabetical order. Okay, so this is that. We can do a confusion matrix. So we can pull out the predictions from the fit, and then we can compute a confusion matrix like this. So I'll say squirrels and then predicted class like this. Like so, and we see here, so now we're here looking at our confusion matrix. So it's not great, right? But at least we are getting them mostly right. Doing better than guessing, one hopes. Okay, so let's look at here. So the squirrels case, remember, is the majority case. There's a ton more here, and we are predicting most of the squirrels correctly. This is still a pretty big proportion, right? If we look at the other way, here's no squirrels, and no squirrels there's many fewer of them, but we at least are not predicting, like this prediction here, we're not predicting everything to be in we're not predicting everything to be in squirrels. At least we're getting some of these to be no squirrels predictions. Looks like if I were to divide those numbers out, it's still a little easier to identify the majority class, even after the downsampling. So that's good, interesting to see. So that's us evaluating this. Before we just wrap up, let's very quickly do a look at the variable importance here. This is a linear model, so we can just pull out the coefficients of the linear model. I find the easiest way to do that for a GlimNet is to use the VIP package. I can just do this. Like this. So this gives me which things are in the negative and the positive direction. And let me just throw in a quick visualization. I am going to group by sign there. I'm going to take the slice max of the importance. Let me take the top 15 on both sides. So now I've got 30. I'll ungroup, and then let me just make a quick plot. I'm going to put importance on the x-axis, the variable on the y-axis. I'll say fill equals sign, and like so. I usually like 8, and I will do facet wrap vars sign. And I think I'll need to say scales equals free y. Is that right? Okay, let me fix this up a little bit. Let me say fact reorder here. Variable in order of importance. And let me, like some things I might do here. I might take on the, let's take away the y-axis. Let's take away the fill axis like that. Okay, that's pretty good. So let's look at this. So this is what our model used to make those predictions. So if you want no squirrels, you should put your bird feeder in the desert on some pavement or in an agricultural area. So these things are about when this is true about your feeder, it pushes the prediction more in the direction of no squirrels. If you have a lot of nearby feeders and the housing density is high and you have woods, deciduous woods, your yard is woods, you have mixed woods, or you live in a swamp, then you're gonna have squirrels. You're gonna have squirrel problems. So this at the end tells us our model, which we can argue had middling, unimpressive performance, but it is what it is. We see this is what drives the predictions in one direction or the other.
All right, we did it. We used this data set on bird feeder sites and whether squirrels come or not to predict, like whether a squirrel will come there and learn what kind of, what drives the predictions in either way. Because of the class imbalance, we tried both not doing any subsampling and then downsampling our data, throwing away a lot of the majority class each time we fit something to be able to create a model that more accurately can learn both positive and negative classes. This is a common approach to try to deal with it, and the result that we got is also often what commonly happens. Our accuracy drops, our log loss drops, things that metrics that measure the model performance as a whole are worse after we do this. But we do give up that performance in the pursuit of being able to more meaningfully identify both the positive and the negative class. So I hope this was helpful, and I'll see you next time.